Okay.
So,
okay. So welcome to our third, last but not least, talk of the day. And it's a pleasure to have Alexei Mailybaev from IMPA, Rio de Janeiro. And he's going to talk about hidden symmetries in fluid dynamics. Very good.
thank you, Elena. Let me just. Oui. Okay. So, hello, and oui, what I did. Okay, no control at all. Let's go. So thank you very much for coming. So I'm going to talk about and thank you for the invitation. So the pity not to be inconvenienced, of course, but what to do. I'm going to speak about symmetries. So it will be okay. So I will remind first briefly what are the symmetries. So what symmetries we'll be talking about. So we will be discussing the symmetries which correspond to Euler equations. There's something. Just give me a second. There's something bad happens with my. Okay, it works. So it will be symmetries about Euler equations, which also assume to be symmetries of the developed turbulence in the inertial interval. So essentially, we will be focusing on Galilean group. The Galilean group is all combinations of temporal translations, so the evolution, spatial translations, rotations, and Galilean transformation. So assuming that you in a full space, in your dynamics in the d-dimensional space. And then there is a special scaling group. So scaling group corresponds to change of scale of time. So we rescale time and we can rescale space. Together they give a group that we will be interested in. There are some other symmetries, but we will be only focused on these symmetries. So the next slide shows the setting. So essentially, the results I'm going to present will all be fully rigorous. And in order to make them rigorous, we have to make an assumption which is actually jumps over all the trick equations about partial differential equations. Essentially, most of the equations discussed here in the conference about uniqueness, existence, and so on. So we assume the two things which are in these first two lines. The first, that there is a configuration space well defined. So the point x, it will be always x. So x is a point in configuration space, which is for fluids, it means that normally it is a velocity field at a given time. So the full state of the system at a given time is given by x. So it's you think of velocity field, and we will be interested in measures. So the configuration space is also given together with a measure in the space, so probability measure. Then there will be, we will assume that there is an evolution operator. So it's in dynamical systems, it's called flow. So it's a map which maps the initial condition to the state at time t. So we assume that it exists, so it defines a group or semi-group. So essentially, its assumption of all the results is that there exists unique solution. So this is essentially what's written here. So we don't care. We will not care about existence. We assume that it is there. Then the measure that we will consider is assumed to be invariant. So invariance of the measure is that it doesn't change by the flow. So this push forward by the measure by the flow, but at any time is the same as before. So it's a what's called statistically invariant state. And then you can formalize. No, first of all, when we consider fluid dynamics, so it is when it is about velocity fields, we can write symmetry operators as maps. So we consider symmetry operator at given time, t equals 0. So every symmetry is given by the map. So space translation, rotation, Galilean transformation, temporary scaling, and so on. So temporal scaling is just dividing by constant, the velocity field by constant. So it's a change of the velocity field by the symmetry at the fixed time. We only need a fixed time because changing from one time to another time is already in the flow operator. So we have a collection of maps. So the collection of maps, which is a map from a configuration space to configuration space, so which assumed to be measurable, and so on. So essentially, what is important is commutational relations. So, for example, you can see here how these operations are commute. So, for example, if you can take temporal scaling as TS, temporal scaling subscript, with flow phi t. So, if you first apply temporal scaling and then evolve it with time t, it's the same as first evolve at time t over a and then make temporal scaling. So you see that there is this commutation relation. They do not commute, strictly speaking, but they almost commute. So there is a different parameter here. So they do not commute, but there is a relation, and the list of all relations is written here. Most of them do commute. So, for example, the flow commutes with special translation, or flow commutes with rotation, and so on. But there are some that do not. And this table actually gives everything we need to know about the maps. So this table was created by using the actions of symmetries for the velocity fields. But in fact, this table is already self-sufficient. So whenever you have this table of the commutation relations, you fully define the group of symmetries on your configuration space, and you can forget about what was what is exact representation, what is the original system. And this is exactly our setting. So we assume that there is a group which includes also evolution, that is phi t, and this group satisfies these relations. So we will work with this group. So that two important issues of this group is on the first line. So if you consider symmetries, what is the relation between symmetries and evolution? So the operation phi t, which is translates system from initial condition to time t. So it turns out that it commutes with all of them but two. So there are two symmetries which do not commute with the flow. One is time scaling. So if you scale time in the beginning of the evolution or at the end of the evolution, it's not the same, because if you scale it in the beginning, it's the same as scale it at the end, but then you have to evolve it over different time. And another symmetry which do not commute with flow is Galilean transformation, because if you make Galilean transformation in the beginning, it's the same as doing it after, but then you also have to translate it. So there are two symmetries which do not commute with the flow. So we will be working with these specific two symmetries. This slide just shows details of this non-commutational relation. It just shows that if the left side shows the left relation. So whenever you first scale time and then translate at time t, or whenever you first translate at time t over a and then rescale time, and you see that at the end you get the same field. So it's just justification of this commutation relations, and also for Galilean transformation, just to show that everything works correctly. On this slide gives so why at all we do all this stuff. So first of all, I have to introduce slightly weaker notion of symmetry, which is a statistical symmetry. So before we had a symmetry which maps solution to solutions. So whenever you have solutions, the symmetry is a map which gives you another field which is certainly in some sense define a new solution. So statistical symmetry, how we define, is a transformation of measure that preserves its invariance. So statistical symmetry will be transformation of measure of measure with the property that if the measure was invariant before, then it will be invariant also at the end after the transformation. So it in particular doesn't have to be a map. It's not it's just transformation of measure. So this will be statistical symmetry. Okay. In particular, all the symmetries that we considered before, all these groups, so each of the map, its push forward gives us the statistical symmetry, because it's, except for Gaussian transformation. So the Gaussian transformation does not, but if it's homogeneous, it also becomes statistical symmetry. So the statistical symmetry is a notion which is a bit wider than just a symmetry. So now, why we do all this question is related ideologically to multifractal theory for developed turbulence. So by how it was formulated by Parisi Frisch. So what they say that we have a family of scaling symmetry. So for each h, we can scale time and space with a certain relation. So alpha rescales time, space, and alpha 1 minus h rescales time. So if the solution is invariant with respect to the scaling, then we have a very nice scaling of structure functions. So all structure functions scale with exponent hp. So everything is self-similar. But now it's not the case for turbulence, because the multifractal theory, it discovered turbulence. It assumed that the flow is self-similar in this way for each h only on some fractal subset, and the full flow is a union of these fractal subsets for all h. So altogether, so the solution altogether in the whole solution, all symmetries are broken, but you can just specify different subsets which are fractal, where each of these symmetries will be restored. So there is kind of duality that all symmetries are broken, but at the same time, all of them are present. So what we want to do is to transform, to make some transformation to the system such that it becomes truly self-similar. So what we will do is we will make a projection of the original equations of original system, such that all of these symmetries, which depend on h, so all this family of symmetries will collapse to a single symmetry, which does not depend on h. And as such, this solution, which was where the all symmetries were broken, they all collapse to single symmetries, so self-similarity will be restored. Okay, so this is idea, and probably I tried to, if you see my video, so I tried to make this toy. I don't know, I have to. I try to make a toy. So if you have something, it is. I have to remove them. So if you have something which is completely unsymmetric, but there is symmetry inside, so maybe you can project it in the right way, like this, and it becomes symmetric. So this is an idea. Yeah. So in short, so you try to find, you know that symmetry is hidden inside. So you just find a projection so that you make it after projection, it becomes symmetric. So this is an idea, and we will try to make it. So we will first do it theoretically, and then I show example how to do it, and also I will show that this is exactly the property that stays behind the intermittency. Okay, so what we will do, we will essentially what we do is completely algebra. So it's not partial differential equation; it's purely algebra, and we will work first just with free group elements. So the h will be the HA is the scaling, time scaling. So changing time by scale, dividing time by A. Phi t is evolution, so translating in time, and G will be spatial scaling. And so H, phi, and G, they have this commutation relation. So H commutes with itself, so it's multiplicative group. Special scaling commutes with flow, scaling between each other, they commute. But there is this important relation that this time scaling does not commute with evolution. So, and now what we do is we want to go along the way of constructing quotient group with respect to time scalings. So remember, when you have a group, you can try to construct a quotient group with respect to subgroup. And the necessary condition is the subgroup is normal. I won't recall you what does mean, but for example, if it commutes with all elements of all the elements, it's normal. So there is some certain property in order to make a quotient. And this property is not satisfied here. So this non-commutativity means that you cannot make a quotient of the full group, this 3-element group, with respect to the time scaling. But what we do that despite you cannot do quotient, we try to do it. So in a way of doing quotient, you can make a halfway. So you cannot go all the way to the end, but you can make halfway. It turned out that it's exactly what we need. So we will not be able to derive a quotient group, so which means that there will be no symmetries for the quotient, but there will be symmetries for the measure. So we lose the symmetries in the original sense, but we still will keep symmetries in the measure sense. So what means doing the quotient with respect to the subgroup means that you define equivalence relation. So you say that two states are equivalent if they are related by time scaling. So X and X prime are equivalent, two different fields. If you just by changing time scale, by changing scale of time, you can put them together. And then we will work on equivalence classes. And here immediately you see the problem is that equivalence class are not they are not invariant under the flow. So if you evolve X to time t and evolve X prime to time t, they will not be any more equivalent. So we have to do something about this. And what we do is we use this relation, commutation relation, which is show that they do not commute, but there is something. And what you can see this from this picture. So X is your original initial condition, and then you evolve it with time. So at time t, you come here. Now take another state which is equivalent. Evolve it with time. You see that when you evolve at time t, you are not on the same class. But if you evolve it slightly longer, you will come to the same class. So essentially, you have to evolve it to AT time. So it does it mean that adjusting the time, you can repair equivalence. And this is what is done with this definition. So what we say is that what we will do is for each equivalence class, we will find one representative Y, and we will form the representative set. So it's a representative set is a set of which contains one representative for each equivalence class. So whenever you have your system X, you can always project it to some, by time scaling, you can project it to some state of this Y set. And there is this P is a projector. Okay, so there is a projector, and then there is also, and this representative class can be uniquely defined by arbitrary measurable function from space of states to positive real numbers. So now we will consider this system on the So we'll try to project our dynamics on this representative set. It's not trivial because you see that the problem is the time at each when you project each trajectory evolves at different times. So we have to, in addition to the projection of the states, we have to also introduce new time. And this is what's given in this theorem. So essentially, it tells that you can define a flow on a representative set explicitly. So it's given by projection and by the original flow, but taken at time tau. And time tau is defined by this integral relation with respect to original time. So it's time tau, it's a solution dependent time, and it will be a flow. So you can define the flow on the representative set. Flow means that it satisfies it's a group or semi-group with, so phi t1 composed with phi t2 is phi t1 plus t2. So it's evolution. It's a new evolution of the new system, and which is very important, the new flow also has an invariant probability measure. So if nu was an invariant probability measure for the original flow, we can have a new the invariant measure also for the projected flow. And it's obtained by projection, so see, and by nu a means time change for the measure. So you have to make this division. So this is more or less standard in the dynamical system. So what it tells is that we can project the system to the representative subset. Okay, and the next theorem is exactly what substitute the quotient. So quotient group. So quotient means that so at the moment we define so this psi tau would be the quotient of the original flow. So flow is an element of the group. So its quotient version will be psi tau. So what will be the quotient version of the spatial scaling of G? So this theorem tells that you cannot define a map which will correspond to the spatial scaling. So the spatial scaling as a map will disappear, but you can define this G star, which will be transformation of measure. So you can, so what it tells that whenever you have invariant measure nu and G nu for the original flow, you can define the measure nu and G star nu for the projected flow, and G star nu is given by this explicit relation. So it's some transformation, the absolutely continuous transformation of the original measure, and then you have to push forward it by this combination of projection and G. So the spatial scaling will disappear as a map in the configuration space, but it remains as a transformation of measure. So it remains as just statistical symmetry. It's not anymore symmetry, but it is still statistical symmetry. And here where the main fact comes. So it tells that whenever you have original symmetry, so original symmetry, which is exactly what I said. So any combination, if this original system was symmetric with respect to any combination of temporal and scaling symmetry, it will be symmetric with respect to this new G star symmetry in the projected sense, but not vice versa. So it can be symmetric with respect to G star, but not symmetric with respect to any original symmetry. So this is where the hidden symmetry comes. So the new G star is now a hidden symmetry. So it's symmetry which is weaker than all the symmetries that it comes from scaling symmetries, but it's weaker than them. So all the original scaling symmetries can be broken, but G star can still, but the system can still be symmetric with respect to G star. So there is so in that sense, it's a new symmetry in the projected equations. So so this is the algebraic framework. So now let's give I will give you the example. So how it works. I will skip for now this Gaussian transformation part, so probably we'll come back to it later. But what I'm going to show you is a solvable intermittent shell model. So how to make a shell model where you can completely solve. It will be fully intermittent, so all this scaling exponent will be nonlinear dependent on P, and you can prove, you can compute them and prove. So you can compute them and prove that these are scaling exponent rigorously using this hidden symmetry. So this is a new shell model. So essentially it's given by this equation. So this is equation du and dt, and then there is this form. It's not quadratic form, but it has the right scaling. So it has a scaling. So it is second order homogeneous in U. So and the coupling is a bit specific. So it only couples to the previous shells. So there is no coupling to the further shells, but there are coupling in the previous shells. So you see it's kn un squared by the factor which is uniform to homogeneous of degree 0. So it's just ratio, the function of ratios, and f is given by some specific complex function. So just depending on r, which is a function of angle. So there is this explicit form of the equations which we will solve. So they're made by some back engineering. So you will see that they can be solved explicitly. So this system has a right symmetry group. So it has a symmetry group of the scaling symmetry group of all the equations, and it doesn't have energy conservation. So we just skipped, we omitted the energy. And the idea is that omitting the energy, we can make it solvable. And on the other hand, essentially there is no strong indications that energy is at all important for the intermittence, because you see that all essentially, if you look through the attempts how people, physicists, try to also mathematicians try to explain intermittency, you will see that energy actually does not even come to the consideration in these studies sometimes. Okay, so we will solve this system. So first of all, first theorem is a theorem that ensures that there is a flow. So there is a uniqueness in existence. So it tells that for any initial condition where all components are non-zero, there exists unique solution for all times. So it's global in time, and moreover, for each shell variable will be bounded for all times, by some constants, which in principle may depend on initial conditions. So the proof is simple. So essentially, what we do is we take, instead of variables u, we consider ratios, and new times, which are defined by differentials in this way. And this is exactly the transformation that we considered before in the algebraic sense. It is a projection to the representative set. So here this is A, which we had in projection, and this is new time, which we also had in the projection. So this is actually nothing else. It's a projection to the representative set. And whenever we consider these variables, the original shell model equation, it reduces to the single ODE on a complex plane. So we can solve it explicitly. And since we can solve it explicitly, and it's the same ODE for all variables, only each variable lives with respect to each own time. So then directly you get global existence in units. So this is first part. And the second part is about structure functions. So if you, I just remind you that this was our original shell model, which was fully defined by some function r, which depends on angle. So it's a function which depends on angle, positive function which depends on angle. So what we need is the average mean value of this function. So we assume that mean value is transcendental number. So if it's transcendental, then for any initial condition, so arbitrary initial condition which is not zero, we can define structure functions, and just in a normal way how it's always defined for shell models. And this structure function is exactly power law. So it's ln in the power zeta p. So ln is 1 over kn. And exponents are given as logarithms of the moments of the function r. So this graph that we will use in example, so you see that it's generally intermittent. So generally zeta p depends non-linearly on order of the structure function. So the proof is well, hits will two pages. Essentially, the proof uses the same transformation to the projection to the representative set, and the fact that all equations become uncoupled, but this uncoupling is actually a bit fake because they are uncoupled, but each of them in its own time. So in fact, they're coupled because times are coupled. But at the same time, for each n, we can solve it explicitly. You can see the first term goes to 0, So in that way, you can see, you can find an attractive invariant manifold. Also, because of no coupling to smaller scales, you can just cut the system at any n and consider the first n shells, because they're not coupled to others. Then we can use all theorems for dynamical systems. So whenever n is finite, our invariant manifold is a torus, n torus. And then we can make some transformation. Essentially, we can write the solution in terms of original variables, and we can make change of variables. And actually, we show that after the change of variables, the dynamics on the invariant torus is quasi-periodic, and quasi-periodic with rationally independent frequencies. So then directly there is a theorem, that Kronecker's theorem, that tells that in that case the system is uniquely ergodic. So our system is uniquely ergodic on an infinitely dimensional invariant manifold, and with uniform measure, with a uniform invariant measure. So then computation of the structure function is straightforward because of unique ergodicity. Unique ergodicity means that any initial condition, not almost all, just any initial condition works. And then we can substitute temporal average, but phase average, and just directly compute structure function and see that the power laws and find the scaling exponents. Okay. And here is just numerical test. So we took a very specific function. We computed all, for this function, you can compute all scale exponents explicitly, just give a formula. So in terms of this combinatoric expressions. And then this is a graph for the scaling exponent. So you see it's strongly intermittent. So it's a nonlinear graph. And here is the result of numerical simulation. You can just solve the system numerically for a long period, for a long time, compute structure functions, and compare the numerical results with numerical. So they perfectly match. So it's just numerical verification that the proof is correct. But the proof is reverse. And then finally, this is for whoever did simulations of the shell models. This is how it looks like. So these are modulo of shells, variables as a function of time, and you see that it looks rather close to the Sabra model, for example. And whenever you take higher and higher shell numbers, like U10, U20, you see that intermittence emerges very strongly. So you have that peaks which are separated by these laminar windows. So, and everything solvable, everything computable. So now only I would like to mention, so this is directly linked. So the reason why it is solvable and why we have intermittency is because of the hidden symmetry, and hidden symmetry is hidden in this equation. So you see, for all n, it's the same equation, which means that whenever in original system had this family of scaling symmetries which depend on age, the new system after changing variables have a scaling symmetry which is correspond to changing index n to n plus m, where m is arbitrary integer number. And this transformation, it looks simple, but in fact, it's quite a non-trivial, non-linear transformation, because this involves non-linear change of time, which is given by this formula. So this is a non-linear transformation, which is a symmetry of the system written in this special variables. Okay, so I first come to the intermediate conclusion. So I will conclude on what I said, and then I will give some perspective to other results which were done in this framework. My internet is okay. So what we did is we considered the group of symmetries. So all the group of symmetries, assuming that there is a well-defined flow operator, and then we noticing that there is a that the flow does not commute with temporal scaling and with Gaussian transformation. So at the moment, it was just temporal scaling. It turned out that you can normalize system on a representative set. So you can do kind of quotient construction. You cannot do it completely because of exactly because of this relation, because they do not commute rigorously completely. But you can make a halfway, and what you obtain in the result is that you obtain a well-defined system on a representative set with a symmetry. But the symmetry is not anymore transformation. It's become a symmetry, statistical symmetry. It's become a symmetry which maps invariant measures to invariant measures. Okay, so this is what, and we can see that we saw on the example that whenever we have this symmetry, we have also intermittence. So this goes to some further results, and actually this is a quite large branch of results. So it's in these 4 papers, where the 3 papers, these 2, 3, 4, they're finished. It's accepted but not yet appeared. And the first, which is central theoretical part, it's an archive. So so you can see this concept of hidden symmetry into. So let's split it into parts. So first, the basic series. So we can make a quotient construction for the scaling symmetries. This is what I just described. So by projecting on equivalence classes, so by removing, in fact, time scaling from the system, we can get a hidden scaling symmetry, which is weaker than the others. In fact, exactly the same, very similar procedure can be done also for Galilean symmetry. So you can consider equivalence classes with respect to Galilean symmetry and try to remove it from the system. And in this case, it's different. I think, yeah. So I think I will show a little bit details about Gaussian transformation, because it's actually quite interesting. So this Gaussian transformation, the commutation relation involves also space translation. So if you first Gaussian transform and then evolve, it's the same as if you first evolve, then Gaussian transform, and then shift in space. So this relation implies that you cannot make exactly the same transformation as we did before, but still we still can project our dynamics on a representative set. Only in general, we do not have a statistical symmetry, but we will have statistical symmetry under one additional assumption, which you derive from this algebraic group theoretical derivation. So you from commutation relation of the group, you can derive additional condition for the existence of the statistical symmetries. And it turns out, surprisingly, that whenever you rewrite this condition in terms of for the fluid dynamical system equations, it's exactly incompressibility. So the incompressibility condition for the incompressibility of a fluid is coincides with the condition for existence of the hidden symmetries with respect to Gaussian transformation, which are coming directly from exclusively from the commutation relation. So there is this coincidence. I think it's very amusing, because one comes directly from algebra, another comes from physics, and it's just coincidence that they exist. Well, not such a coincidence. So this is the second part of what the basic theory can tell, is that you can also make the quotient-like construction with respect to Gaussian symmetry, and it requires incompressibility, and essentially what it gives is a quasi-Lagrangian representation, so, which is known for physicists. So it also comes from algebra. So we can make it the basic theory. So now application is the first application I showed. It's a solvable shell model where you can have equations which are deterministic. You can solve them, and they are intermittent, and you can find all analytically all exponents. Then this procedure can be applied to Navier-Stokes Euler systems. So this was shown by Simon Talabar last week. This was his talk, so this is our joint work. So you can just make all this procedure explicitly for the Euler and Navier-Stokes systems to see that this symmetry exists. And you can verify it numerically. So we had some numerical verification. Who attended the talk may remember. So numerical verification just show that there is a rather good indication, numerical indication that despite all the symmetries, original scaling symmetries are broken by intermittency, after you make the transformation, the system becomes scale invariant. This third part is quite interesting. So it turns out that hidden scaling symmetry directly implies power law scaling of structure functions. And this I will not have no time to tell. So this in this large paper one. So you can define structure functions. It turns out that you can define structure functions in purely algebraic form. So without referring to the equation of motion. And this definition will correspond to structure functions whenever your system is fluid dynamics. And you can prove that at the moment when the system has a hidden scaling symmetry for the statistical symmetry, all structure functions are power laws. And typically they are anomalous. So the second step is that you can even write you can show that scaling exponents can be obtained as eigenvalues. So it's Perron-Frobenius eigenvalues for certain linear operators which are constructed using this measure. And then you can test these last properties on the numerically on Saber-Shell model. So this was done also in the literature, in the course. Okay, I'm quite fast. I think I finished. Thank you very much.
Okay, thank you very much, Alexei. Does anybody have any questions? You can raise your hand or you can ask in the chat. You can unmute your microphones. Yes, Giorgio.
So just to understand, you have, I mean, in a physics sense, you have global symmetries where you transform a solution into another solution and Noether's theorem holds. And then you have gauge symmetries, which are, in a sense, redundancies of the description. And in particular, Noether's second theorem holds that derivatives, if you have a functional, derivatives of that functional obey differential equations. If I understood you right, the symmetry is acting on a measure. So probably it's more like a gauge symmetry, right? There is no conserved quantity associated with it.
Even worse, I would say, because even gauge symmetries, these are symmetries which apply to the fields. So it's a transformation of field. So the hidden symmetry is not a it cannot be written as a transformation of the field. It's a transformation of the measure, of a probability measure. So it's a probability measure on the space of the field. So we only have a symmetry which can be applied to the probability measure as a whole. We cannot apply it to each state.
Yeah, but gauge symmetries kind of function in a similar way. I mean, what happens is that the measure is independent of gauge transformations.
Well, whenever you have any symmetry which applies to the states, like gauge symmetry or global symmetry, they also define, of course, the transformation of measure automatically. But what we have is a transformation of the measure which cannot be written as a transformation of the field.
Okay. Okay, thanks.
And it turns out that whenever your measure is symmetric in this way, it automatically implies intermittency.
Yeah, no, this is something similar. Something similar happens in gauge theories. In gauge theories as well, with what is called renormalizability. Is this connected to the study of turbulence with renormalization group methods, because there is certainly a connection of gauge theory with renormalizability.
Well, I would like to understand this question because I was asked something similar in that spirit, but up to now, I have nothing except for more than very vague intuition. So you see, so I cannot formalize it in any.
Because this power law intermittency is, it's similar to renormalizability.
Yeah, of course. Yeah. The power laws are similar. So the way how you come to it it doesn't seem to. I don't see the connection so far.
Okay.
It would be interesting to see.
Okay. Are there any other questions? Okay. Then let's all thank Alexei and all of the speakers for the day for a very interesting